In the previous lecture, we've done module 3. We also completed module 1 and 2. We now have module 4 and 5 left as part of the syllabus. Module 4 is slightly based off of module 5. So we'll be starting with module 5 first, and then we'll cover module 4, which is relatively smaller than module 5. There is a main topic in module 5. It's mainly about Turing machine and a couple more topics. Starting with Turing machine, first of all, we have studied different types of grammars. We've studied regular grammars and we've made finite automatas for that. We've studied the grammar for push-down automata, which is CFG, context-free grammars. Okay. Now, Turing machine is a machine, as the name states, and the grammar that is accepted by Turing machine, the grammar that it works on, is on unrestricted grammar, okay, or recursive grammar. This is type 0 grammar, and it is the most vast grammar, and it allows the most complex relationships to be made. So these are the tuples, okay. Now, what is a Turing machine? In a Turing machine, you basically have an infinitely large tape, okay, which extends in both directions. The tape has symbols on it, okay, like we've been seeing, the input symbols that you read, and there is an FCU, okay. This is a finite control unit, and it has a read-write head that points to a certain symbol. You can move this head towards the right or the left, one step at a time, okay. And it reads the input, and it can also write the input over here. So it can edit the same input, and it can create a new symbol in place of the input depending on the type of question or grammar or whatever the machine is supposed to make. And again, the tape extends infinitely at both sides, okay. We have a certain set of inputs, okay, based on the alphabet. Once the inputs are done, okay, since it's going infinitely, there is obviously a certain finite length to the input on each side of the tape. Once the input string is completed, it is followed by blank, okay, the blank symbol B. You can either use B, or we have another symbol that I'll refer to later on. That symbol represents that the string has ended over there. Once you encounter B, okay, capital B, which is also why the blank symbol, you don't usually use B, because it might confuse you with the terminals and non-terminals. There is a symbol for that. So once you encounter the blank symbol, that means the string has ended, and infinitely you just replace it with blank. The transition function is as follows for the Turing machine. Before we look at the transition function, I would recommend looking at the tuples. We have these tuples over here, where Q again is the a set of non-empty states. You have the alphabet, and then you have the tau, okay, which is a set of tape symbols. These are tape symbols, okay. And then you have the transition function. You have the initial state. You have the blank symbol, and you have the set of final states. Final state are of two types: accepting or rejecting state. And the blank symbol that is used is this. Here you have it. It is similar to this, kind of like the backspace sort of symbol. This is the symbol that is used to represent blank in the tape, okay. So the transition function in a Turing machine is as follows: at any state along with the tape symbol, okay, you can move to another state based on the tape symbol, okay, whether you're reading or writing, along with any option from moving left or right, okay. So the and in terms of your states, in the way we represent it in questions when we're answering, when we create a function, you write it as follows, where q0 is the state that you are at, and this is the input symbol, and you transition to the next state, okay. And the second symbol over here, x, is what replaces a, okay, what replaces the input. And lastly, you have the move direction. An example which can be followed, this language a n b n, okay. This was not possible using regular grammar, okay, when we were making it in a finite automata, because you do not have the ability to store n. And since this is an infinite one, we studied the language has a possibility that it is not regular. We used PDA for this, but we can also implement this using Turing machine. Here is some theory about Turing machine, okay. It has a read write head, and the input tape goes infinitely when input symbols and rest of the tape is filled with blank symbols, okay. Yeah, so this basically means that you have the input symbol and the rest of the tape is filled with blank symbol because it goes infinitely. The blank symbol can be this or B, or you can also use the dollar symbol. Read write head can read input symbols, edit or update the symbol. This is what I meant. You read and you can edit the symbols as well, the input, and it moves one step to the left or to the right. Okay, the functions are performed by the finite control unit, the FCU, which controls the read write head. Now, looking at an example, okay, to understand how you can make the state diagram for the Turing machine. So for the language 0 1 clean closure 0. Okay, so what does this mean? We've studied this in regular expressions in when we were creating the expressions. Over there, this would mean, since there is a clean closure on 1, that means 1 can be null. Okay, 1 2 and infinitely. So this means you have 0 and 1 and 0. The most basic string would be when 1 is null. So you'll have 0 0, you'll have 0 1 0, 0 1 1 0, 0 triple 1 0, and so on. So for this, when you're making a Turing machine, you start at Q 0, just like you do in all other automatons. And when you encounter 0 as the input symbol, okay, you transition to Q1, okay, and you have the X. You replace 0 with X and you move one step to the right on the tape. So what this means is the input was 0, the 0 was edited or updated and changed to X, and you moved one step to the right on the tape. Okay. Now at Q1 you will encounter n number of ones. Okay. So for 1, what are we doing? Whenever we encounter 1, we are replacing the input symbol with Y, and you're moving one step to the right again. So we're moving from left to right. Okay. So every time we just move towards the right. Okay. In this case. So the most basic symbol was 0 0. Hence at 0 you replace it with X and you move towards the right. Then you get 0 again, you replace it with X and you again move towards the right, which takes you to Q2. Okay. This is the most basic language. Hence the machine should accept this language because you want it to be accepted. So you're going to create an accept state. Okay. And since once you've moved right, okay, you've moved right twice. What does that happen? You were over here on this 0 in the tape. Example, this is the tape. Okay, you were here at 0. You replace this with X and you move to the right. Again, you're at this 0, you replace it with X, you move to the right. Now what's going to happen? If this was the only input string, then now you would be waiting at the blank symbol. Okay, hence once you are at the blank symbol at Q2, okay, you will replace the blank symbol with blank. You don't need to put anything over there, right? You just leave it as blank and move toward the right again, okay, and accept. Hence that means if you have 0 0, your machine will accept it. Now for ones, okay, the moment you transition for 0, we've understood this one. You put X on the tape, X0 becomes X, and you move to the right. Now you are waiting over here. If you get a 1, what happens is you replace it with Y and you move to the right. Okay, if you get a 0, you go to this state, else you stay on this one. For double ones, you stay on this one 3 times, 4 times, and so on, just like we did in our finite automatas. Okay, again similar, except now you also need to make a reject state, right? Because possibility is your string starts with 1, okay, or it just ends at a single 0, okay, or after two zeros you get a 1, okay, or three zeros. You can't have three zeros either. You can only have two zeros in this. Okay, so at 1, okay, so you will replace it with 1 and you'll move right, which is reject. Okay, so that means the string is unacceptable. Again, even in blank, that means you don't have any string at all. You cannot have a null string in this language. This says the minimum string is 0 0. So at 1 or at null, if the string is just blank, okay, you reject it. Again at 0, and then it just ends over there. That is blank, that means reject as well, because you cannot have a single 0. At 0 0 and then you're getting 0 again is wrong. You can only have two zeros, hence again you'll send it to the reject state, and after two zeros you can't have a 1. The 1 has to be between the two zeros. So again at this state also you'll send it to reject. Similar to our DFAs and everything that we've made, you have to specify these cases for reject and accept in the state diagram. Okay, so this is just the explanation of what is happening in the diagram. Next, we have a few points over here about the Turing machine. On the TM is basically Turing machine. Okay, on the Turing machine tape. Okay, further ahead we'll be looking at the term TM, and then you write another capital M. That means the Turing machine M. That's basically you naming the machine as M. Okay, just wanted to clear that beforehand. On the Turing machine tape, we read the current symbol, and based on machine function, we replace old symbol and move head left or right. Okay, this is the basic thing. The TM halts. Okay, this is important. The TM Turing machine halts when it comes across certain symbol or strings for which function isn't defined or doesn't exist. What does this mean? This means is this for Turing machine halting. Okay, there are two possibilities in a Turing machine. Either it will continuously go through these loops again and again. Okay, because how is that possible? Because we have an infinite string, so it can infinitely keep on going through them, right? Or it's just gonna halt at a point when the transition function is not defined. What is happening? You're moving the head left or right on the basis of the transition function. Okay, if that in itself isn't defined, then there is no transition that is going to take place and you'll halt. Okay, if that halting occurs at accept state, okay, that means you have that means the string has been accepted. If it goes at the reject state, that means the string wasn't accepted. Okay, so this is the difference. And how does it stop at the accept state? We say it over here. As for the final state, since there are no functions defined for them, the TM halts at the final state. So once you reach the final state, you don't have any function defined over here. You don't have any transition over here. Hence, your TM will halt over here. Now, what is Turing computable? Okay, a function of domain D, okay, a function f of a domain D is Turing computable if there exists some Turing machine M. Here we have a TMM. That means if there exists a Turing machine called M which has the following tuples, okay, such that this statement, okay, so I'll be explaining this. What this means is Q naught W, okay, you are starting at Q naught, okay, and you have an input string W, okay, and based on the computation of the Turing machine, you reach a certain final state QF for which the solution or the function is applied on W and you get an output. Okay, this is what this means. And then you have QF belongs to a set of final states, okay, and all W belongs to the domain. I've just explained it over here. It starts at Q naught with input W on its tape, okay, means after finite steps, okay, after a finite number of steps over here, clean closure means finite steps of the Turing machine, okay, it reaches final state QF from a set of final states. The output on the tape is FW, okay, which means that the Turing machine M computes a value for F on the input W. Okay, simple as that. Looks a bit complicated, but once you break things down onto smaller parts and try to understand, it gets much easier. Now we're looking at an example of computing the sum of two digits using a Turing machine. Okay, we have had this question in a past paper, so it is important to look at this. Don't get confused if the past paper question says using unary notation. That is very simple. In unary, what you basically do is you use the number of ones to calculate the digit. So if you have three ones, it's three. If you have four ones, it's a four. If you have two ones, it's a two, and so on. Okay. So in unary, what we're doing here is we're adding two positive integers x and y. Okay. So based on unary notation, again, ones represents the number. Okay, we use 0 in between two numbers to separate them. Okay, hence if you have 3 plus 2, okay, you say 1 1 1 and 1 1. So 3 plus 2 is 5. Okay, so if you just combine these two numbers together, you're gonna get 5, right? And if I put a 0 between the two, I can tell that the 0 is separating two numbers. 3 ones means 3 and 0 is separating it from two ones, which is 2. Fine. Just this is how you are gonna handle problems. This is a machine. Now, like we studied before, the Turing computable formula, you have to know how to apply it. Okay, what it means is, again, like I told you, you'll always start at Q naught, you'll go to QF, right? Wx is the input string x, okay, which is input integer x, okay, 0 in between, and wy, okay. So you have the string y and you have the string x, or the number y and the number x separated by a 0, and on the basis of the machine, okay, in a number of finite steps, you reach a final state where w is x plus y, and I'll tell you why the 0 is at the back. Okay, so answer is achieved when 0 is removed from between the two numbers, right? Once you send the 0, you remove the 0, okay, then you'll have 1 2 3 4 5 5 ones together. That means you have solved it, right? When you count the numbers, it'll be 3 plus 2 5. Simple as that. So you have to remove the 0. How are you going to remove it? We are going to follow the following steps. Okay, first of all, we'll have the number of states. Okay, Q0, Q1, Q2, Q3, Q4. We will set Q4 as final state. We have tape symbols 1 0 and you have the blank symbol. Okay, 1 and 0, as we know, we're just counting in ones and zeros. The 0 is separating and the 1 is counting the number. Okay, so we have the tape symbols 1 and 0. Blank is always going to be there. So our first function will be from Q0. You're starting at Q0, and obviously your string starts at 1, right? You have a certain number of ones over here. So for every one that is encountered from Q0, you are gonna replace it with 1. So you're gonna keep 1 over there, and then you're gonna move right once. Okay, and the moment you encounter a 0, okay, so from q0 you encounter a 0, so you'll move to q1 and you'll rewrite 0 as 1. Okay, so what we're basically doing is it is 1 1 1 0 1 1, right? So you came on the first one, okay, you replace it with 1, that means you just don't change anything. So you move right and then you move right, okay, and then you move right again. Now for this function you need some different function, right? You are encountering 0 at the input tape. So what we are going to do is we're going to replace this with 1, okay, and we're going to move right. What that happens is the number of ones has increased, right? Okay, we have an extra 1 over here now. So what you're going to do is you're going to reach the end of the tape and you're going to make this a 0, which is exactly what is here in the function. So w is x plus y, and you move the 0 from between the two at the end. So that way you will have the number of ones together. You've removed the 0, right? Same concept. So which is why when we encounter 0 in the string, okay, we are going to change state. First of all, from q0 you'll go to q1 and you're going to replace the 0 with 1 and you'll move right, okay. As it says, find 0 and replace with 1, move right. Then at q0 you again do the same thing like you did at q0. At q1 you're going to do the same thing you did at q0, which is if you have a 1 you're going to replace it with 1, that means you're not changing it, and you're going to move right, okay. You'll keep doing this until you reach the blank symbol. So if the input symbol is blank, okay, at q1 the input symbol is blank, you are going to go to q2 and you're going to move left. Now q2 state is going to remove the 0, okay. So why are we using these states? Q0 was to iterate through the um, first x number, x integer, okay, and q1 is iterating through the y integer, okay, if we look at this carefully. And then q2, what q2 is going to do is going to change the extra 1, okay, it's going to remove the extra 1. So from q1 you shifted to q2, you kept the blank and you just move left. What happens is you reached this point of the string and then you went here at the blank state. So now you're going to keep the blank as it is because you do not want to change anything over there, and you're going to move once left to this one, okay, which has to be made 0, okay. So at q2, okay, when you encounter the last one, okay, you are going to go to q3 and you're going to change it to 0. Again move left, and then from q3 for every one you're going to keep moving left and you will reach the start of the tape, okay. Like this is just resetting the position so that once you're reading it again, you know where you're reading the number from the beginning of the string, okay. Again, once you encounter a blank symbol, which is again going to be on this side of the tape, on the left side, so you're transitioning over here from here to this one, then this and so on, you get to this end. So lastly you're going to change the state once again and you're going to move once right, okay. So you're going to keep the blank symbol as it is, okay, don't no change to that. You're changing state to q4 and you're moving to the right. Again, like our Turing machine definition said, q4 is one of the final states. It's a set of from the final state qf, okay. It's part of the final states, right? I mean, we have a single final state in this. So q4 is the final state, hence our Turing machine will halt, because there is, now you can see there is no function defined for q4, okay, because you don't need a function over there. It's done. You're done with the string. That once you reach q4, that means your string is accepted, hence machine is completed and the string is accepted. And now, this is all there is to Turing machine. I've explained how you can make a state diagram. I've explained what it is. I've explained what Turing computable is. Turing computable, again, is basically anything where you can apply the function, this function, okay, for a given for the given tuples, and create a Turing machine where that certain function can be solved. An example was this, which is we've seen this, okay. So now we have linear bounded automaton, okay. This is the same as Turing machine, but in this, okay, the tape is not infinite in length. Instead, it is bounded, okay. Just like it says linear bounded, okay. We have a linear tape and it's bounded by a linear function. And this is a non-deterministic Turing machine with a single tape, okay. It has the following tuples. We have two extra symbols in this, and what these symbols do are they are these left and right blocker markers, okay. They block markers, or they just tell you where the tape ends, okay. So input tape, for example, if it has n cells, okay, you have the FSC is the same thing as the read head, okay. And what happens over here is you only have a read head for the input tape, okay, and the writing is done on the working tape, okay. You have a single input tape which has n cells, and the working tape is k into n cells, okay, k times n, and k is a constant, which is specified by the property of the machine. So that depends on the machine. It's not related to the input tape. Okay. The reading tape, okay, the one that is connected to the input tape, the reading head that is connected to the input tape is read only. Okay, it moves from left to right only and is read only. So these are the two rules. It moves from left to right. Okay, it doesn't move in both directions. Turing machine you could move left and right. In this one you only move towards the right, while the other head, which is at the working tape, can read and write as well. Okay, input tape is read only and moves to the right. Working tape head is read and write. Okay, now uh, this is the definition for a language that can be accepted. So for any string w belonging to the alphabet minus the, like, the start and end symbols. Okay, clean closure. um, and then the rule given is q naught. Okay, and the string between them for a finite certain steps will take you to q. Okay, which is another state. Okay, belonging to the final state or whatever, depending on the machine, alpha and I. Now, this is it for linear bounded automaton. I haven't really seen any questions on this, but if I do find one, I will definitely guide you through these steps of solving a question. This is mostly theoretical, and yeah, CYK algorithm is, again, it isn't part. I haven't seen it any questions, so I don't think there is any reason to study this. If you do want to go through it, you could refer to the NISO channel. Okay, not sure of the full name of that channel, but yeah, they have explained it fine over there. Or you could go to any other channel and try to understand it. Now, the other theoretical part of Turing machines is variations in Turing machines. So first of all, we have the multi-tape Turing machine. Okay, has multiple tapes as the name states. Okay, and heads as well. For each tape, you have another head. Okay, one head per tape, and it is more efficient than the single tape, but not more powerful. So see, it is the same Turing machine, it's just more efficient because it's got multiple tapes, but the power of the machine remains the same. Then we have the non-deterministic TM. Okay, which we just saw. It was the linear bounded automaton, has multiple transitions for the same state and symbol. Okay, accepts input if any path leads to accept state. Okay, same power as the deterministic TM, but it is faster. The multi-track TM, okay, has a single tape, but the tape is divided into tracks. Okay, and it is used to simulate extra memory. It's similar to the virtual memory sort of concept. Okay, and then we have the two-way infinite tape TM. Tape is infinite in both directions. Okay, semi-infinite is it goes in either one direction. Okay, infinitely in either one direction. It's finite on the other side. This is the concept that we just studied in the basic Turing machine. Now, apart from variations, we also need to know what a universal Turing machine is. So this is a general purpose Turing machine which is powerful enough to simulate the behaviors of any computer, including any Turing machine itself. So basically this is, as the name states, a universal Turing machine. It's a machine powerful enough. It has lots of states. Okay, like lots of states. Okay, like we're dealing with 4 or 5 states over here. It has lots of states because it can actually simulate the behavior of any computer. Okay, so it tells you the computing power of it. That is it with module 5. This was all there was. Okay, and yeah, we will let's continue with module 4 because that too is not as lengthy. So module 4 is undecidability and computability. Again, this is related to Turing machines. First of all, we have the term halting. What is halting? We studied this earlier in module 5 as well. A Turing machine halts or stops when it reaches a final state, okay, or when it reaches a state Q for which the function is not defined. Okay, it is possible that in some Turing machines they never halt. Okay, so I told you this as well because there is an infinite tape. There is a chance that in some of those Turing machines you do not halt because it may never encounter the function which is not defined. Okay, it might keep looping through because of a certain type of language. And now these languages, this leads us to two types of languages: recursively enumerable language and recursive language. Okay, recursively enumerable language is a language L, okay, belonging to the alphabet clean closure, where there exists a Turing machine M such that the language is accepted. Okay, the language L is accepted by the machine. This is recursively enumerable. That means the language will be accepted by the Turing machine which is what I told you earlier when we were discussing what a Turing machine is. It is based off of type 0 grammar, which is REL, recursively enumerable languages, fine, and it's based on recursively enumerable grammar. Now, a recursive language is when L is a language L belonging to the alphabet, okay, clean closure, such that there exists some Turing machine TM, okay, some Turing machine M, which if the string W, input string W belongs to language, then the machine accepts W by reaching accept state and halting. If it does not belong to the language, then M halts without reaching the accepting state. Okay. So this is the difference between recursive language and recursive enumerable. Decidability. Okay. This is basically the definition of decidable. Okay, whether something is decidable or not, what it means is that a problem will have two answers. Okay, and it is only decidable if the corresponding language is recursive. Okay, that means, I mean, if you have two answers, what is it, yes or no, right? And what is there in the recursive language? We have W belongs to L or W does not belong to L. Okay, so that is called decidability. Okay, now, is decidable if corresponding language is recursive. If it is not recursive, okay, then the language is called undecidable. A decidable problem is also called solvable problem, because if you can decide something, then you can actually solve that thing. Now, the Turing machine has this problem known as the halting problem, okay, and this problem is solved using a technique called reducing technique, and it is used to prove undecidability of halting problem of the Turing machine. So basically, halting problem is related to decidability and undecidability in a Turing machine. We will refer to this statement to understand what it is. This statement is known as the reducing technique. What you do is you reduce it into parts. So if you have a problem A, okay, you have some issue which is A, and it is reducible to problem B. So you can, change it up a bit and, shorten it, simplify it, and it becomes a problem B. Okay. And if solution to problem B, okay, if you have a solution to problem B, okay, you can solve problem B, then you know that this solution can be used to solve problem A. Fine. This is called reducibility technique. So if A is a problem and it is simplified to problem B, if you can find a solution to problem B, then you know you can solve A. Okay. Now the theorem states is the halting theorem. Okay. The Turing machine halting issue is that when you have a machine M with a string W, okay, the Turing machine M halts on input W. Okay, whether it halts or not, okay, this certain feature, like this certain answer, will M halt on W or will it not? Okay, this is undecidable. This is what the theorem states. Okay, now you have to prove this. Okay, how will you prove it? We will be going through with a negative test. What does that mean? You will assume that this theorem is decidable. Okay, you have to prove that it is not possible. So if it is not decidable, then it definitely means it's undecidable. I mean, that's pretty much logical. Okay. So what you're gonna do is you're gonna create a machine, Turing machine M1. Okay. And in TM1, okay, you will apply halt. Okay. You will apply the halt and let M1 have a halt eventually on all string W in the machine. Okay. And if it does, then we will create a Turing machine M2. Okay. For which we will give the input of M1. Okay. And the Turing machine M1 acts on this input. Okay, if M1 rejects it, okay, so if this, it doesn't halt, or it does not, it if M1 does not accept this string, okay, this certain data, okay, then M2 will reject it. Fine. M2 is working on M1 and M1 is working on a certain set of on a tape, or whatever input you're giving to the machine. Okay, so M2 is working on M1, okay, and M1 is working on the tape, the input that we've given it. If M1 rejects it, okay, then obviously M2 will reject M1, right? If M1 accepts it, then what we're going to do is we're going to simulate the TM, okay, on the input string until M halts. So first of all, it's the acceptance issue. Will M1 accept it or not? If it does accept it, you will wait for M to halt. Fine. If it rejects it, first of all, then M2 will reject M2 rejects. If it accepts, then you will wait until M halts. If M has accepted, which means if M has halted at an accept state, then M2 will also accept it. Fine. Else M2 will reject it. Now what is all this? It's kind of confusing, but just think of it as a machine that is solving an issue, okay? And whatever output is giving, okay, you're using another same machine that is working on that output, okay, and on the machine, to determine if the machine will work or not. Okay, now it's making me doubt this as well. Let's go for the easier explanation. We have the question of halting problem. The question is, given a Turing machine M and input W, okay, we have to, the question is, will this machine M halt on W or will it run forever? Okay, will it not halt at all? The halting issue. Like I said, the halting theorem states that it is undecidable. Okay, meaning what this means, this theorem means that no Turing machine can decide this for all cases of the inputs. Okay, maybe for some cases you can tell that yes, it will halt, or no, it will not halt. You can decide that. Okay, but it is impossible to do that for all cases. What we are going to do is we're going to try to do that. Okay, so what, for that we have created M1, and it's, we are assuming that it solves the halting problem. You give M1 an input, okay, and it says yes, okay, then that means M1 halts on W, and if it doesn't, then it doesn't halt. Okay, it keeps on going infinitely. Now you create another machine which uses M1, okay, and the input to this M2 will also be the string that was given to M1. Fine, you run M1 on that string and you ask the question, will it halt? Okay, if M1 says no, that means M2 will tell you that it was that M1 has rejected it. Okay, if M1 says yes, okay, then you are going to simulate M on W. You are going to simulate the machine on the string. Okay, and by this it means when M1 says yes, it means it is accepting the string. Okay, and it's running on the string. Once it starts running, now you'll wait for it to halt. Okay, if it halts, okay, accept or reject means halting and not halting. Okay, if it halts, that means M2 is accepting it. Okay, M2 says that M has accepted it. If it rejects, then M2 tells you that it's rejected it. But how is this possible? Okay, here M2 is telling us whether M accepts or not. Okay, that means M2 solves the acceptance problem. Okay, so what does that mean? M2 is deciding it. We said it's undecidable, but M2 is deciding it. Okay, but that's not possible. The ATM, okay, equals, this is another theorem for the machine M and string W. M accepts W is undecidable. Okay, this creates a machine that decides ATM, okay, which is undecidable. Okay, so that's the whole point over here. The machine is deciding, okay, the outcome which is undecidable, hence the contradiction, so the assumption is wrong. You do not need to write this entire proof. Okay, this much is enough. You have to state the theorem. You don't even need to mention this. This is just for understanding. So when they ask you about the halting problem, you just have to tell them that you're using the reducing technique. Okay, and this is the theorem, and this is the proof. That's it. These 5 points are the proof. Okay, this is for explaining. If you still didn't understand, then I mean, considering that we've just got about 24 hours for the examination, I'd prefer you just, learn these steps. There's just 5 steps, and yeah, that should help you. Now we have another undecidability issue, okay, which is PCP, the post correspondence problem. The task in this, okay, is to choose a certain order of the list. You have a list, okay, of X and Y, and you have to choose a certain order of the list, okay, repeating the units of X and Y if required, such that the string of X, okay, and Y are equal. So how do you understand this? For example, you have two lists. X goes from x1 to xn, and Y that goes from y1 to yn, of non-empty strings. Okay, you have a certain string in them, 0, 1, a, b, or whatever. Okay, so the PCP is to determine whether or not there exists a sequence from I1 till IM. Okay, so in X, instead of 1, 2, 3 till n, you are going to replace it with I. Okay, so I1, IM, and so on. The order of the index I, okay, the indices I has to be the same for X and Y. Okay, look at the, oh my god, sorry, look at the example. Over here you have X, A, B, A, and B. Fine, and you have Y, A, B, and B, B. This is X1, X2, X3, Y1, Y2, Y3. From X you have X as replaced as 1, 2, 3, and Y as 1, 2, 3, but these strings are not equal, hence this is not solvable. Similarly, you have another example where you have B, B cubed. B cubed basically means 3 B's, okay, and BA. And for Y you have 3 B's, BA and A. What you're gonna do is you're gonna take M as 4. This is trial and error, so you just have to, play around with it and you try to find out. Just take a pencil, sit down, make pairs, and try to find out how you can make equal strings out of them. Taking M4 means you have I as I1, I2, I3, I4. Okay, I ranges from 1 till M according to this range. Okay, I is from 1 till M. So I1, I2, I3, I4. Fine. And this is X1, X2, X3, right? What you're gonna do is you're gonna arrange I1, I2, I3, I4 such that you will repeat units of X1, X2, X3. So over here we came up with a certain pair of I1 is 2, I2 is 1, I3 is 1, and I4 is 3. So that means 2, 1, 1, 3. So the second pair, the first pair, the first pair, and the third pair. Okay, similarly, second pair, first pair, and third pair. Okay, 2, 1, 1, 3. X2, X1, X1, X3. And Y2, Y1, Y1, Y3. When you arrange them, you will see BA and 3 B's, and then BB, BA. Similarly, BA, 3 B's, okay, BB, and BA. This is what we had, BB, BA, okay, BA, B cubed, BB, BA. So you see they're equal. That means this is solvable. Okay, this is PCP just tells you the problem of decidability and undecidability. It is a theorem for that. It's an algorithm for that. MPCP. This is a modern modified version of PCP, and the only difference is over here we had the capability. We were allowed to start with X2 or X3 or anything, but in MPCP you will be starting with X1 and Y1. Okay, so for example, you want to arrange the string. Okay, so you will have to start with X1, which is B, and Y1, which is B. So you'll arrange the string in a certain manner where X1 and Y1 will stay in their positions, but X2 and X3, Y2 and Y3 can be interchanged. Okay, this is all there is about PCP. Again, we'll do questions on this from the past papers that will help. Quick covering of the entire syllabus. Okay, this is a blueprint for TOC. We've had Chomsky hierarchy. Type 0, we just studied it. Recursively enumerable language. Okay, it has unrestricted grammar. It makes REL languages, and Turing machine is used in it. We have context sensitive, which is type 1. It is context sensitive grammar. You have context sensitive language for that. It is accepted by linear bounded automaton. You have type 2, which is context free, for which you had push down automata. Okay, and regular, for which you had finite automatons such as DFA, NFA, epsilon NFA, MFA as well, MDFA, sorry. You have automata theory, which you have these. You have the Turing machine. You have variations of Turing machine. Okay, then we have language classes. These are the 4 levels of languages. Okay, and remember, undecidable languages, okay, the whole point of them, the whole reason why we have the other theorems, the halting issue and everything, is because they're not recognized by any Turing machines. We have 2 normal forms for context free grammars, which is CNF and GNF. We studied those. We have the decidability issue. Okay, the acceptance problem is ATM, and the halting problem is there, and we have the reductions. Finally, our other topics were PCP and MPCP. We have pumping lemma for regular languages and context-free languages. See, regular languages we had XYZ distributions. In context-free, all you have to do is you just have to up it a bit. Okay, pump it up a bit. It's pumping lemma, so yeah. You don't take XYZ over here. Instead, you take W equals UV X YZ. Okay, it's a much larger string. Okay, and then you just have to print you have to pump up V and Y. Okay, and accordingly you have to show that it does not belong to the language. And yep, that's it. This is all for module 4. Let's refer to the PPT a bit. Okay, we have studied all of this. Yes, post correspondence problem and MPCP. Now this is a small topic, so we'll quickly go through this. Partial functions and total functions. Okay, a partial function is where you have a function, okay, of x and y, and for every x there is at most one element of y. So either you have no y or at least one. Okay, example is you have a function from r to r, given that it is for fr equals positive root of r. Okay, this is a partial function since it's not defined for negative. Okay, You partially have values for real numbers, but for negative you do not. Okay. Similarly, a total function would be where x and y, okay, is there. F is from x and y, and for every x you have a unique y. Okay, so for every x there is a y. Example again, same r to r, okay, and this is mod r. Okay, this means whether the value is negative of r or positive r, you have a certain value for the function. Okay, it is defined. Okay, we consider total functions f from xk to x, okay, where x is 0 to so on, okay, or it belongs to a certain alphabet. We denote 0 1 2 3 as natural numbers, okay, and the variables by summation, by sigma. These are our terminals that we've been using throughout the time. Xk is a set of k tuple of elements of x. Okay, so basically x number of elements in the tuple, that's all it means. Partial neutrino functions may continued. You have example fmn, okay, where m minus n, so this is a partial function because you do not have it defined for negative. Okay, similarly when you have gmn where m plus n is the function, then it is defined for all natural numbers. Okay, so this is a total function. Partial or total function f from xk to x is also called a function of k variables denoted by f, x1, x2, and xk. Okay, for example, you have x1, x2 in f. Okay, and this is the function. Okay, so this is a function of two variables. Okay, and if you solve it, you put 1 and 2, you'll get the answer 4. 1 and 2 are the arguments of f, and 4 is the value. Okay, similarly it can be done for the tuples. Okay, for the terminals that we've used all over the time. Now we have initial functions. Okay, these are primitive recursive functions. Sorry, primitive recursive functions over n and over the sigma. Over n you have three types. This is zero function defined by zx equals 0. Okay, so whatever value you have in x, the answer will be 0. This is a zero function. I mean, the name states zero function. You'll get 0 as the output. Successor function s, okay, is defined by sx, means x plus 1. So whatever value you've inputted in the function, you'll get the successor value, the next value. Projection function, okay, uni, okay, uin power n is defined by ui power n x1 till xn. So you have n x values of x, and the ith value will be the output. Okay, so xi will be the output. And for initial functions over sigma, we have a difference in the name. Okay, so nil x, similarly you get a null. Okay, null value lambda epsilon constant ax. Okay, cons ax, whatever you want to call it. I don't think it is constant, it's cons. Okay, we'll just go with it, which means with x you will add a before it, and again similarly for b you'll add b before it. Here's an example. If you have z7, it's a null function, so it's a zero function, so you'll have 0. S4, this is a successor function, so you'll do 4 plus 5, 4 plus 1 5, and u, it has a tuple of 3. Okay, and you need the second position, which is 5, hence your output will be 5. Again, now for the alphabet, okay, you have nil AABB, which will give you nil. Cons AABB, okay, you'll just add another A, and for this one you'll add another B. That's it. That's all there is to primitive recursive functions. Okay, three types. Okay, you just define them and you give an example, and that's it. Okay, the composition of a function is f1, f2 till fk are partial functions of n variables. Okay, so these are k functions, okay, k number of functions that have n variables each, and g is a partial function of k variables. Okay, so what composition is basically, when you write the g and f together, okay, so you'll just write f1, okay, with n variables, f2 with n variables, fk with n variables inside g. That's it. So the composition of g with f1, f2, and fn is total when both of them are total. An example, everything is easier with an example. So f1 xy, okay, is this, f2 xy is this, and f3 xy is this. So you have your number of variables in this is 2. Okay, xy xy xy. G has 3 variables in it. Okay, since we studied it, g is a partial function of k variables. Okay, so g is xyz equals x plus y plus z. Okay, functions over n. Find the composition of g with f1, f2, f3. So the solution is composition of g with f1, f2, f3 is given by h xy g of f1, f2, f3, which is x plus y, 2x, and xy. Okay, just open the brackets, and this is how you're gonna write it. Okay, again you have to remember the number of variables will be, you will drop z. Okay, because the number of variables will be based on f, not g. Okay, So G has k variables, you'll have k functions inside it. G had 3 variables, okay? So you'll have 3 functions inside it instead, 3 f functions instead, okay? And the variables will be xy, xy, and xy. So you just replace them inside, okay? You replace the functions, and that's how you get the output. So that's it for module 4 as well. We have completed all the topics. These are all the topics of module 5. We have done all these topics, and we've also done module 4, some basic concepts, and we've seen all the important functions that are to be there. If I might have missed anything, we'll be covering that in the question solving sessions. I'll probably make 1 or 2 sessions. I'll solve papers from 22, 23, and 24. 22 and 23 were similar papers, so probably just 1 or 2 different questions from those. And 24 is important. You need to go through all the important topics that we've done. Try to understand how to make all these diagrams, how to make anything. Any doubts, try to reach out. You know where to find us. And yeah, good luck for your examinations, and see you in the question and answer sessions. Thank you.